Yeah, so the last little bit of the chapter is going to be 12.6, where we talk about projectile motion. And I'm not sure if I'm sharing the right screen here. Projectile motion, you did in physics for sure, where you're talking about usually gravity being a constant acceleration. For projectile motion, it's always gravity is the constant acceleration. And so you're using those equations that we derived last time to say, okay, if I have a starting position and an ending position and it's launched at a certain angle, what does its speed need to be so that it hits the target or something like that, right? We probably did a whole bunch of different ones like that. Um, and the nice thing about it, and what's similar to what we did today, is we can split that into an X and a Y, right? And then we can get magnitudes if we need, or we could come up with just individual X distance or change in height Y, right? Rather than doing like a full magnitude of the position that changed, right? That would get a little sticky if we're wanting to do projectile motion. And so that's probably what you did in physics a little bit. We'll play with it a little more in this class. So something like this, a basketball shot at a certain angle. He's got a certain release height. The basketball's at a certain height, or the hoop's at a certain height. He's shooting it at a certain angle. It's a certain distance from the hoop at a certain speed, right? What parameters should the shooter consider in order for the basketball to pass through the basket? And super realistic. I like this example because playing a game of basketball, you could sit there and do some calculus. Uh, no, but you could do that if you were building a robot or something, right? Or if you're calculating how far a missile needs to launch to hit some target far away, right? It's the principle is there, right? So we could change the distance, we could change the speed, we could change the location, how far from the basket he's at, right? So those are all things we consider. Here's another very realistic situation where when the building is on fire, you should probably make sure you're going to hit it exactly in the right spot with your water. So, right, especially when the bricks catch fire. Now that's why I had time to do the dynamics calculations real quick, is because it was just bricks on fire, so it wasn't spreading too fast. Um, right. Uh, but yeah, you could you could come up with the height based on how fast the water's coming out and what angle he's spraying at, something like that, right? Okay, so the idea here, though, what we want to keep in mind is it's really two motion equations. We've got an x equation and we've got a y equation. And we can use our constant acceleration equations for both of them, really. Although, which one will it apply to if we are using constant acceleration for gravity?
Y.
Yeah, the y will have acceleration, the x will not have any. So two of our equations have an a in there for acceleration, which means for the x equations, those two will not be very useful. But in the y equation, we'll use all three of them. And so it'll be the combination of basically those four equations, however we need, the one x equation that is still useful, and then the three constant acceleration equations for the y component. Those will be the ones that we have to play with. And it all comes down to this. This is a way to visualize what I was just saying about the x has no acceleration. So whether you put a ball in a horizontal path, right, the yellow ball in this case, it's shot out sideways and going towards the ground, or you could just drop the red ball. They will both hit the ground at the same time, right? And this is super important because it it almost gets taught to us intuitively wrong. Like you play a Mario game, right? And if you run extra fast, you can go higher, right? Which there's something to be said about like having momentum and your body being able to do more, put more force into the ground to jump higher if you're already moving. But it's not the fact that you're moving, accelerating in the X that makes you accelerate more in the Y. They're totally unrelated, right? Um, so we could actually show this real quick if we wanted to try it. See if we can catch it on the camera. Be interesting. Oh, and I'll have to run and I'm gonna run and jump for you guys. No, I'm just kidding. We're gonna do we'll just try to slide a an eraser at the same time as we drop one at the same time. All right. Let's see. Gotta unblur it here. All right. Let's see.
Yes.
I don't know if this is gonna work that well. Okay, we might be able to show it right here. Okay, I'm gonna put this up here.
I did too. Oriented. That's great.
Not the best view. I don't know how to get this to show right. So if I slide this going that way, we're gonna catch it. Okay, okay. We got this. Now these are too light. They're gonna catch too much. Let's do two markers. A red and a blue for easy visualizing. And is that gonna go that way? The what?
I can hold the camera.
You gonna hold the camera. Oh, that would work too. All right. Yeah, let's have you be the cameraman. Okay, gather around, folks. Let's see this great magic trick. Ready? So we need to be able to see the ground for both of these. Right? You guys probably won't be able to see from there. We're gonna try and show these hit the ground at the same time. So this one's gonna be maybe do it to. Can you bring it this way, or is that like all the room you've got? Okay. Okay, try and show the. So that's gonna be right there, and we're just gonna go like that. Okay, that'll do it. Ready? Okay, so when this comes off the table, I'm gonna drop it. Ready? 1, 2, 3. Oh, there was a slight delay.
So the humans reaction time is 0.75 seconds. So
Yeah.
they're driving, so
That's probably it. Yeah.
0.75 seconds.
Okay. Okay. Here we go. Here we go. That was pretty close. That was pretty close. So, as we've clearly proven, what I want you to remember is that those hit at the exact same time, exactly the same. Just like the balls in the picture, they're going to hit the ground at the same time, regardless of whether one has x velocity or x acceleration. Well, it won't have x acceleration, but if it did, even if there was something zooming it forward in the x, it's still going to hit the ground at the same time because the y acceleration didn't change just because there was x velocity or acceleration. That all checking out?
Change the angles.
Would it? If I threw it up at an angle?
Yeah. So the way to get the farthest horizontal distance, the 45-degree angle.
Okay, yeah, that would change our horizontal distance for sure. But they would still hit the ground at the same time. Well, not if no, I guess if when it was at an angle. Never mind. That wouldn't be the same.
Yeah.
Yeah.
Nice try.
Yeah. Yeah. And they wouldn't have the same starting velocity. All right. So here's how we're gonna play with this. Okay. We'll split it into an x and a y velocity. We'll split it into an x and a y position, right? And the acceleration will only be in the y. So from our acceleration equations, our constant acceleration equations, there's only going to be one that has anything useful left, right? We had one that was like velocity equals the initial velocity plus at. Well, that just tells you if you cancel out a equals 0, that the initial velocity equals the final velocity in the x, which is going to be true, but it's not super useful other than to know that whatever the starting x is going to be the finishing x, right? Then in the y, we have all of them still. Right? I've just placed in there y instead of s, we have y and y not, and just threw on some subscripts to make this. And instead of an a, we have now g for gravity.
But what were we supposed to put in the parentheses? EXE.
Wait.
That one, probably.
There it is.
Yeah, so the initial equals the final in the x. So yeah, those are 3 y equations. And do you remember why I said at the beginning that only 2 of these 3 equations could be used at any time to solve for 2 variables? Are they actually 3 equations?
Fine.
Right. Yeah, we got that third one by combining the first 2. So really we've got 2 independent y equations and 1 x equation. So we can solve for 2 unknowns with all those. Okay, so we'll give it a shot with an example here.